Thanks. Our next speaker will talk about microwave-assisted extraction, followed by two-dimensional chromatography.
Hello. Thanks for the nice introduction. I am really glad today to have the opportunity to share with you some results of my research. And I will go quickly through introduction, objective, results, and conclusion. As you could see from the title, I will talk about FAMES analysis, and in particular, for this kind of an analysis, sample preparation is also important, and in particular, I'm working with microwaves. So I will talk about a bit of this technology that were discovered in 1945, quickly patented, and then in 1947, the first microwave for domestic purposes was sold. Then someone thought, okay, if I can heat my food, I also can heat my reaction. So basically in 1975, the first domestic microwave oven was used for extraction of organic compounds from soil. And then due to the increased interest in this technology, in 1993, more sophisticated instruments started to show up on the market. And today, more and new technology are under development. But what are microwaves? They are non-ionizing electromagnetic waves that range between 300 megahertz and 300 gigahertz, and they are made of two oscillating and perpendicular fields, an electric and a magnetic one. How their energy is transformed into heat? Basically, by two different mechanisms. The first is ion conduction, where basically ion in the sample solution moves following the oscillating electromagnetic fields, and so this movement causes friction with the sample solution, and this friction causes the heat. Something similar happened with the dipole rotation, but in this case, we have molecules in the sample solution that can have a permanent or induced dipole that are randomly oriented in the sample solution, but when microwave energy hit, they try to orient themselves in phase with the oscillating electromagnetic fields. And so once again, this movement causes friction and then heat. This concept is, let's say, more understandable if we are going to compare microwave heating with the conventional one, where basically the heat comes from the hot plate, then is transferred to the vessel, and then to the solution, while in the microwave heating, the vessel is transparent to the microwave, and the solution is directly heated. So you can understand this, it's heating that comes from the inside, and so for the advantages of microwave heating, we can cite direct heating, so it's also high efficiency, short processing time, and also green process, and we also have less heating exposure that it also translates into more security for the users. We wanted to use this technology for the analysis of FAMES. FAMES fatty acids are a basic unit of fats and oil, and their analysis is important for the characterization, determination of total fat in food. It's important for labeling, so for nutritional labeling, understanding the availability of fat, and also for healthy impact, so to understand the correlation with some human disease. For fatty acids analysis, the sample preparation is really important. It's also challenging that involves different steps. First, the extraction of lipid fraction, then derivatization to have the corresponding methyl esters derivatives, and then the GC analysis. In our lab, it was developed a method that goes to merge these two first steps into a one-step microwave-assisted extraction and derivatization with all the characteristics showed. And basically, after 15 minutes, the organic phase that contains FAMES is ready for the injection in the GC. In addition to the sample preparation, we also optimize a chromatographic analysis to increase the throughput of the overall analysis. And basically, we use the flow modulation comprehensive two-dimensional chromatography coupled with an FID, using a septocolumn property of Sepsolve specific for FAMES analysis. Why GC time GC? Basically, really often we receive comments, let's say from person X, that comes and say, I do the same in 1D. Why are you using two-dimensional chromatography? Basically, because from a chromatographic point of view, FAME analysis can be challenging if we deal with complex matrices. So basically, using 1D, we may face some limitation. For example, we need long capillary column, or also 2 different GC run with different stationary phase. You can agree that it's expensive and also time-consuming. While with our method, we can have a lot of benefits. The first advantage is the use of flow modulator. If maybe you already know, but in the animation it is showed how it works, I want to point the advantages, the key benefits that we can have with this kind of modulator. First, it's consumable free, and this allows also to reduce the running cost if compared to the cryogenic modulator, where we need a cryogenic fluid that is not that cheap. And also, with this modulator, we don't have volatility restriction. So basically, volatile compound can be modulated as efficiently as semi-volatiles. And also, we can have the same number of compounds separated if we compare with a cryogenic modulator. So in a multidimensional workshop, I don't have to list the advantages of GC time GC, but I want to point it out, the one that I had using GC time GC for FAMES analysis. Basically, thanks to the enhanced separation and reduced exclusion, at the first glance, looking at the chromatogram, we can see which peaks are not FAMES and which peaks can collude in a same running time in 1D. Then, for FAMES analysis, using a second dimension separation, we can obtain a really structured chromatogram. And so we have a really easy pattern to read, let's say. We can easily see the saturated, monounsaturated, 2 double bonds, 3 double bonds, and so on. And last but not least, thanks to the increased sensitivity, also trace compounds are easily detected. All of this with an excellent repeatability of the instrumental analysis, as you can see from the reported relative standard deviation of retention time in first and second dimension, and also the area of the C35 FAMES standard. So now, let's see the objective of the work. There are 2 objectives. The first, it regards the sample preparation. So basically, we want to answer the question, is MAED a reliable alternative to official methods? And the second, it's about the chromatographic analysis. Always, person X often comes to us and say, okay, I like what you do, but the quantification in 2D is not reliable. And so here, to answer this question, and with the comparison in 1D and 2D, we want to find the answer to this question and say, we can do it. So for the first objective, we are going to compare MAED, so one-step assisted extraction and derivatization, two official methods. This is an extension of a previous work where this comparison was made on these matrices. We chose another batch. Here, all the characterization of the methods that we compared. We have the AOCS official methods that use conventional heating and BF3 for derivatization, and MAED that is one step and also goes to replace BF3 with a less toxic agent that is an acidic solution of methanol. So here, as we can see from the percentage profile of saturated, monounsaturated, and polyunsaturated, all the 3 methods performs exactly the same, so the results are completely aligned, and also if we are going to compare the single fatty acids detected in all the matrices. So for the first case, we can say that MAED is confirmed as a reliable alternative to official methods. This is only a little extract of the paper that we recently published, so if you want more information, you can search or scan the code. Here, basically, we are going to compare other microwave-assisted methods that we basically included in the comparison. Otherwise, you can contact us. For the second objective, we want to compare 1D and 2D for FAMES analysis. And for this comparison, we choose a really complex matrix that is a muscle samples. As you can see from the 2D chromatogram, you have a little spoiler of how many compounds are present, FAMES. And always person X comes and say, I can do it in 1D. And I say, yes, but you have to use a column like this, that, okay, you can have good separation, but the runtime, it's 1 hour and 20. That is not convenient, for example, for a routine lab that needs to process a lot of samples in a short time. So let's take a column that is widely used for this analysis. You can, the specification, you can reduce a lot the running time, but what happened? All the analytes are not well separated, and a lot of coelution occurs. For example, here, of 40 detected peak, only 18 was identified. If we compare the same, of course, chromatogram into D, we can see clearly which peak coelutes, which peak are not FAMES, and also with this comparison, the identification in 1D is even a bit easier. Which is the difference? That in 2D, you can detect more than 100 peak and identify 82, and in 1D, 40. So if we are going to compare the percentage profile of the 18 common fatty acids in 1D and 2D, we can see basically that the quantification is comparable. But let's see a little particular. For example, this coelution. We saw that here they are comparable, but in 2D we have more information. What we are going to do with this information? We can have a more precise idea of the content of saturated, monounsaturated, and polyunsaturated fatty acids. You can usually find this information on the label of the food that you buy. And you can see that because of coelutions, in 1D, the polyunsaturated are overestimated. Also, if you want to calculate nutritional values that are calculated based on saturated, monounsaturated, polyunsaturated, omega-6 or omega-3, basically you can see a discrepancy between the results in 1D and 2D because of the same reason. To conclude the part of results, we also evaluated the greenness of the methods, of the sample preparation methods, and basically the official methods received the lowest score, while the MAED the highest. And a little note here is that, this matrix that we use didn't take into account the use and the benefits of GC times GC. We also evaluated the blueness of the methods with the metric BAGI, that is basically the evaluation of how practical is your method. All the methods are considered practical because they scored more than 60, that is the value to be considered practical, but also here the MAED has the highest score. So to arrive to the conclusion, we can say that one-step microwave-assisted extraction and derivatization is comparable to official methods, but it's also more green and practical. Why? Because we have a high throughput with microwave, because we can process 12 samples each 15 minutes, so 48 per hour, or even more if we use different rotors. It's sustainable, and it has been demonstrated that it can be used for a wide range of samples, and it also promotes automation and security, going to minimize energy consumption and the use of less toxic solvents. We also can confirm that the quantification in 2D is comparable to the quantification in 1D, so it's reliable. But also we have other advantages with, for example, the structure chromatogram in GC times GC can make us not use an MS, and also that the flow modulator is more energetically sustainable than the cryogenic one. I finished a bit earlier, but no, I didn't finish. I want to thank my research group from the University of Liège and the University of Turin, you for your attention, and I will be happy to answer your question, not before inviting you all to the third to the third edition of Advances in Separation Science that the Group of Analytical Chemistry of Jean Blou is organizing, and that will occur on the 12th and 13th of June. We also have one-day courses on the 11th that you can choose between SPME or GC courses. And for more information, you can check the website or scan the QR code.